A smart city relies on a constant flow of millions of overlapping data points. Drones, autonomous vehicles, and sensors must continuously exchange information to function. Building the infrastructure for this environment requires enterprise-grade hardware. Minima is a Layer 1 blockchain actively collaborating with global semiconductor and industrial titans like ARM and Siemens to secure this data. Looking at this standard trading chart, Minima's market capitalization sits at roughly $2.18 million, a figure that stands in sharp contrast to the multi-billion-dollar valuations of its development partners. This valuation indicates a specific analytical error. The market is evaluating an industrial hardware protocol through the lens of a consumer software application. Retail traders map price action based on hype and consumer user acquisition, while remaining blind to the physical deployment of deterministic architecture. The actual development of this network is happening on factory floors and inside advanced hardware fabrication facilities. Retail investors are looking for decentralized finance applications designed for human day traders, while Minima's engineering team is embedding their protocol directly into the silicon of commercial hardware. Measuring Minima by retail crypto sentiment misinterprets its target market. It is an infrastructure play designed for the machine-to-machine economy. The machine-to-machine, or M2M economy, is a system where physical devices, sensors, and vehicles transact and verify data independently, without human oversight. Traditional, human-centric blockchains fail under these conditions because they are too slow, the fees are too high, and they rely entirely on centralized cloud servers for validation. In a dense urban environment like London, millions of edge devices operate simultaneously. The geography of the M2M economy requires immediate, localized processing. An autonomous drone navigating a flight path or a self-driving car assessing a collision risk cannot wait for a cloud server in another country to validate a decision. The latency risk is unacceptable. For the M2M economy to function safely, trust must be a native property of the machine itself. Applying existing major Layer 1 protocols, like Bitcoin or Solana, to autonomous machines reveals a severe architectural flaw. This diagram illustrates the hub-and-spoke model. Millions of edge devices route data back to a small cluster of centralized validators, creating latency issues and single points of failure. If the connection drops, the autonomous machine is paralyzed, its data is unverified, and operations compromised. Minima replaces the hub with a hyper-dense, flood-fill, edge consensus mesh network. Every device connects directly to its neighbors. In this mesh, every connected device operates as a complete, constructing, and validating node, removing third-party bottlenecks from the data verification process. Distributing the validation workload across the entire device population ensures the network remains operational even if the surrounding infrastructure fails. This raises a clear technical challenge. Running a full proof-of-work node usually requires massive computational power. A smartphone or an IoT sensor cannot process that workload without draining its battery. Minima solves this constraint with its foundational innovation, transactional proof-of-work, or TX-POW. Traditional proof-of-work is a competitive race. Miners deploy massive server farms to solve cryptographic puzzles faster than anyone else to win a block reward. This split view demonstrates the difference. TX-POW is collaborative. Instead of a server farm racing to win, every device performs a tiny fraction of cryptographic work just to send a transaction. Because the work is distributed widely, the energy requirement per device is negligible. This background hashing utilizes less than 2% of a modern smartphone's daily battery capacity. By making cryptographic work collaborative rather than competitive, the protocol eliminates the financial incentive for centralized mining pools. The network secures itself through sheer global scale. Power is only the first constraint. The second is storage. Traditional blockchains record every single transaction permanently, swelling the ledger to hundreds of gigabytes, far too large for an edge device. Minima handles this data bloat using a state compression mechanism called the cascading chain. The protocol actively prunes standard blocks from its history, retaining only the superblocks, mathematically proven records of the total accumulated work on the network. Furthermore, Minima uses a Merkle Mountain Range database. Instead of holding the entire global ledger, a node is only required to keep the cryptographic proofs for its own specific coins. This aggressive compression reduces the size of a fully operational validating Layer 1 node to roughly 300 megabytes. Fitting a full node into megabytes of space is what makes the transition from software applications to physical silicon possible. This transition from software theory to physical hardware reality is defined by the 2026 prototype launch. The core hardware innovation involves embedding Minima's C++ client directly into an ARM processor subsystem, housed within a field-programmable gate array board. The hardware features custom accelerators, specifically dedicated SHA-3 cryptographic hashing cores that are etched directly into the silicon fabric. Offloading this computational workload to dedicated silicon achieves a 100-fold increase in the device's hashing rate, while freeing up the main CPU for real-time machine control tasks. This silicon integration allows commercial drones to execute precise autonomous maneuvers within industrial facilities, utilizing quantum-secure Winternitz one-time signatures. The drone hashes and timestamps its specific flight decisions locally, directly on the chip, without requiring verification from the cloud. For industrial regulators, this creates a tamper-proof compliance log that guarantees accountable machine autonomy. Integrating the node into the silicon fabric turns decentralized trust into a physical property of the machine, separate from the vulnerabilities of software-level applications. This hardware infrastructure is powered by a specific economic engine, the native Minima token. The supply parameters are strictly defined. There is a hard cap of exactly 1 billion tokens. Because there are no centralized miners to pay, the protocol has zero ongoing inflation. The primary economic lever regulating this supply is a mechanism called the burn. This counter tracks the network's maximum supply. During periods of network demand, machines must burn a small fraction of a token to prioritize their transactions. This amount is permanently destroyed. This mechanism ensures that as network utility scales and machines process more data, the total circulating supply of the asset systematically decreases. Projecting this model into the near future reveals the impact of ARM and Siemens chips reaching mass commercial adoption across smart cities, autonomous vehicles, and industrial IoT. Millions of embedded AI agents and sensors will generate continuous high-frequency transactions to coordinate and verify their operational data. This introduces a severe financial asymmetry. These machines do not read social media. They do not care about retail market sentiment. They do not panic sell during market downturns. As millions of sensors and AI agents programmatically burn Minima to prioritize their data flow, the network generates continuous transaction volume against a fixed supply. The current $2.18 million market capitalization is the blind spot of a retail market looking at the wrong metrics. The protocol's architecture ensures that future adoption will be driven by machines. The most sophisticated investors are positioning themselves before that programmatic surge begins.